have Paul Arpin from the physics department, who's the advanced student. Started with the program from the beginning in the fall of 2008. He's a PhD student as a student in the physics department with Professor Monet and Kaplan group. He received his bachelor degree in physics from Harvey Math College in Claremont, California, and moved here directly from there. He's today going to tell us about generation and applications of ultra-fast coherent software. So, welcome.
Thank you, Ariel. Good afternoon, everyone. Thanks for coming to the talk today. I appreciate the opportunity to tell you a little bit about what we're working on over in my lab. So I'd first like to start by acknowledging some of the many collaborators we've worked on these various projects, both here at CU and also at some of these various other institutions. Of course, my advisors, Margaret and Henry. And then in particular, I want to point out two collaborators from my group, Tenio Potminchev, and Mingcheng Chen, who both played a pretty big role in the infrared phase matching that I'll be talking about. So in the talk, I'll tell you about how we're able to generate coherent soft X-rays by using nonlinear optics with femtosecond lasers. I'll show our results of the first spatially coherent tabletop soft X-ray light source. And then, depending on time, I'll talk a little bit about some of Matt and Dan's recent results extending these coherent diffractive imaging techniques. Because one of the important applications of the stuff I'll be talking about is going to be combining our new tabletop soft X-ray sources with these imaging techniques that they've been developing. And so I think a lot of you have kind of thought about some of these kinds of problems before. But as you want to start to push to study things on the nanoscale, things that have features with nanometer to tens of nanometer size features, of course, if you want to use an optical microscope, you're getting to be well below the wavelength. You're getting much smaller features in the wavelength of your light. And so, of course, you won't be able to resolve the features. So I know some of the people here, Sean gave a nice talk a couple weeks ago about some other games you can kind of play to start getting out some of the structure of things in these very small features. But the technique we use is instead we're going to go to soft X-rays where the wavelength of the light we're using to illuminate the sample is short enough to actually resolve nanometer size objects. And this has a couple of advantages. The X-rays can penetrate thick objects. Like I said, the small wavelength of the light makes it possible to image small features in a full field image. And actually one of the pretty unique features of X-rays is the presence of elemental absorption edges in this region of the spectrum. So here we plotted a couple absorption lengths. This is essentially the transmission of some different materials in the soft X-ray region of the spectrum. And anywhere you see one of these sharp edges, that's going to correspond to having your photon come in with an energy just right to kick an electron out of the inner shell of an atom. And because each of these, every element has a distinct set of elemental edges, you can do. So each element has a distinct set of edges. And also the local structure around the edge is going to depend on the chemical state that your atom is in. You can do imaging both with elemental and chemical specificity. On the other side, we're going to look at how do you capture the fastest dynamics in the nano world. And so if you want to capture dynamics faster than your eye can see, what's the first thing you do? You take a really fast camera shutter, and you take a series of images, and then replay those images in a much slower time scale so that we can watch how things evolve in time. And so more modern high-speed cameras, instead of taking a really fast shutter, what you're going to do is take a very bright and very fast flash of light that you repeat, again, a series of those and take a series of images to resolve these very fast things, such as a bullet going through an apple. And so as we start to push down to the time scales of atoms vibrating and rotating we're going to repeat that sort of technique. We're going to take very fast flashes of light. In order to do that, you're going to want to use ultra-fast optics, and so ultra-fast lasers. So what we want to do in our group is combine these two. We want to take the high temporal resolution of ultra-fast optics and combine that with the high spatial resolution as well as the elemental selectivity that you get when you work with soft X-rays. And so I'm just going to show a few images of applications in this region of the spectrum, and I'll let you read. So we're not going to have time to go through all of these, but the main point I want to make is that throughout the extreme ultraviolet and soft X-ray region of the spectrum, there's a pretty broad range of applications of ultrafast coherent X-rays. And each of the applications is going to have a specific area of the spectrum where it's going to work the best, whether that's due to the resolution you need, which will determine the wavelength you need, or whether that's due to the fact that you're going to exploit some elemental absorption edge in your material. So one of the kind of the big picture goals, I'd say, of the project I'm working on is to be able to, in a tabletop, in a laboratory scale setup, have a tunable light source of ultra-fast coherent X-ray beams usable for applications throughout this region of the spectrum. Okay, and so I want to zoom in on one of these applications, because this is particularly relevant to the wavelength range I'm going to show. And this is going to be biological imaging. So here again, we're looking at the absorption length as a function of photon energy we're comparing the spectrum of a typical protein, which is made up mostly of carbon, oxygen, and nitrogen, with the spectrum of water. And so carbon's got this strong absorption edge right at 280 eV. And oxygen, the absorption edge of oxygen is out at 540 eV. So if you work between these two absorption edges, you see that water is quite a bit more transparent than carbon, and then also whatever else is in your proteins. So this gives you an inherent contrast mechanism to image things like biological cells. And so one of the interesting features of this is the fact that it relies only on the density of carbon you have in the sample. So you can actually do quantitative imaging of these sorts of samples. And then another point, this is 400 eV, corresponds to a 3 nanometer wavelength. So in principle, you can do something like 10 nanometer resolution imaging of your sample. I like showing this one. It's just it's kind of an older, a little bit older of a paper, but this group on one of the beam lines at the synchrotron use this sort of technique, and they use it regularly. They have more recent results in this, to do a 3D tomographic reconstruction of a cell. And so this group, as well as a couple others, have demonstrated this can be a useful way to look at these cells and study the biology of what's going on. The problem is most of the applications to date have been limited to large-scale facilities, such as synchrotrons, which have limited accessibility to users. And so we'd like to scale this down to a laboratory-type setup, which could potentially extend the application of this technique. And so the approach we're going to take is we're going to use nonlinear optics to convert from to convert our wavelengths to these very short wavelengths. And so I'm sure many of you have worked with second harmonic generation before. This came out of the first demonstration of that shortly after the invention of the laser, where people had high enough peak intensities to start doing nonlinear optics. And it's a pretty simple experiment. You focus into a quartz crystal and then measure and you'll see some second harmonic come out. It's kind of one key point I want to take away from this, and that's because this will come back to this a couple more times. And that's the fact that there's always two aspects to the picture when you're talking about nonlinear optics. And so the first part of that here is going to be the single atom response. Because this is being driven perturbatively, you're going to look at, if you look at the intensity of each successive harmonic, you're going to see it fall off exponentially. And the second component is the phase matching. And so if you actually go and look up this paper, I'm sure some of you have heard the story before, you'll see, if you look, they've got the picture of this photographic plate in there. At 694, at the fundamental, there's a nice bright beam. And at the second harmonic, there's nothing. And that's because the copy editor, at least the way I've heard it, the copy editor saw it, thought it was a speck of dust, and wiped it out. And so the problem there is they didn't understand phase matching. Because if you get the phase matching right, when you coherently build up, you can actually get very efficient conversion into the second harmonic, which would make that a nice bright spot there too. And this is actually, there's a common practice today. These laser pointers are actually 1 micron lasers that are frequency doubled. I think a lot of people. So what we want to do is we want to take this idea of, starting with a low photon energy laser, and up converting to higher photon energies. Take that, see how far we can take it. How short of a wavelength of light can we generate? And the first question should be what happens to the single atom response. I said for these low order harmonics, they're going to fall off exponentially as you go to higher harmonic orders. What does that mean for trying to take this kind of to as far as it can go? So to understand it, just look at what we call the 3-step model for high harmonic generation. That's kind of the simple picture that actually gets a lot of the physics right. We start with an atom just sitting there in its ground state. Apply a strong laser field. And so instantaneously, that laser field is going to bend the Coulomb potential of the atom. And then the electron can tunnel ionize out of the atom. And then once it's just sitting there freely, it'll oscillate in the laser field. And it'll accelerate first away from and then back towards the parent ion. And once it's returned, it can recombine with the parent ion and give off this excess energy it's gained in the form of a high energy photon. And so just for this simple picture, we can get actually a lot of the physics out. We always drive this with a femtosecond laser pulse. So the harmonics we get out are always, if anything, shorter. So typically 10 femtoseconds or less. This happens in each half cycle of this laser field, that the electrons are accelerated away and then back to the atom. So you end up with these bursts of X-rays every half cycle of the laser field. And so if you think about what the Fourier transform of a periodic train in time is, in frequency, you're going to have a periodic train of harmonic peaks. And because this is well out of the perturbative regime, it ends up being something like a plateau, pretty flat intensity as a function of harmonics, up to some cutoff energy, which is going to be the highest photon energy, the highest amount of energy that this electron can gain while it's oscillating in this laser field, which is scales like the laser intensity times the driving laser wavelength squared. All right, and so that's the single atom picture. To get the whole story, you really need to look at, in order to understand how to generate it brightly, you need to look at the phase matching again. And so we need to get the fundamental laser to propagate with the same phase velocity as the X-rays, so that they'll coherently add up throughout this harmonic generation medium and actually get a bright output. And so typically we assume that the X-rays propagate at the speed of light. It's usually a pretty good approximation. And then we come back and look at the different contributions to the phase, to the dispersion of the fundamental beam. And so we start with a hollow core capillary and focus our laser and guide it through that capillary, and then fill it with gas. And so if you write down, you can write down the 3 main contributions to the dispersion. One is going to come from it's a geometric contribution from the waveguide. then there's going to be a contribution from the gas neutrals that we put into the waveguide that slows down the light. And then as you're doing this high harmonic process, you're inherently ionizing the gas as well. And so you end up with some plasma in the waveguide that's going to speed up the phase velocity of the fundamental. And so the things to notice are that the waveguide and the plasma both act to speed up the fundamental laser, whereas the neutrals act to slow it down. So because of this, we're able to balance the different contributions because we've got a contribution from the, because there's a relative pressure term. So by increasing the pressure, we can balance the phase velocity of the neutrals with the phase velocity of the waveguide and get good phase matching. And so when we look at the X-ray output as a function of pressure, you see it's got these strongly peaked, it's strongly peaked, which corresponds to phase matching and efficiently generating harmonics. And so when we do this right, we get out fully spatially coherent beams. This is a Young's double slit of our 30 nanometer source with excellent spatial profiles. This is an image of the spatial profile of the beam. This is because the nice properties of your laser get mapped into your harmonic beam. So this works really well up to a point. The problem is the most natural thing to do if you want to get out a higher energy harmonic is you're going to turn up your laser intensity. And this will work. You'll get out higher energy harmonics. But at the same time, as you turn up your laser intensity, you start to rapidly ionize the medium. And then eventually this plasma contribution speeds up the phase velocity of the laser too much, and there's no balancing the different terms. So here's a couple examples of this kind of approach where we're increasing, going to very high laser intensities. This is a project I worked on, and this is results from another group. And so here we plotted the high harmonic spectrum as a function of photon energy, and we see very high energy harmonics from argon, up to about 540 eV. In this group, again, very high intensities in helium gets up to about a keV. But these, and so you can generate these very high energy harmonics, but this spectrum is a pretty typical looking spectrum in this sort of regime. You've got very bright harmonics at the low energy side, and then you look at it on a log plot and you kind of see some dim harmonics showing up out in the high energy side. And this makes it really difficult if you want to try to do imaging, say there. You've got to somehow get rid of several orders of magnitude of much brighter light. And the other thing is because it's not phase matched, it never gets all that bright to begin with. So this has been one of the big challenges in our field is, we understand how to generate harmonics at very high photon energies, but all of the applications of harmonics have been limited to about 100 eV, because if you take just a standard Ti-sapphire laser, this is going to be your phase matching cutoff at around 150 eV. And so what we're going to propose is that by changing the phase matching, going to infrared phase matching, that actually we can extend the phase matching cutoff to much higher photon energies, which we've demonstrated up to a keV. So this is a full order of magnitude higher in terms of photon energy. Yeah.
What was the thing that made your phase matching cut off where it was? At 100 eV? What is it that causes it to?
Yeah, that's a good question. Thanks. So you can come back to this slide. I don't want to go too much into the details here, but essentially, if you've got these two terms, right? You've got a plasma contribution and then a neutral contribution. Right. If the plasma contribution to your phase velocity becomes larger than your neutral dispersion, then you've got everything has the same sign, and so there's no way. Essentially, the phase velocity of your fundamental becomes too high. And so you can calculate you can do, I didn't show any of these calculations, you can do calculations of the ionization level as a function of time in your pulse. And then, once your ionization level gets too high, you can look at what harmonic energy you can generate at that point.
P on the outside is your gas pressure?
Yes.
Okay.
So the part you're not seeing is the laser intensity is kind of hidden in the plasma level. All right. And so once the laser intensity gets too high, the plasma is going to get too high. You can't. Yes. It definitely depends on. So again, that'll come in on the ionization level. If you have helium instead of argon, helium is going to have a higher ionization potential, so it's harder to ionize. So as we'll show in the figures later, helium is going to have a higher phase matching cutoff.
But there's a third term in there, right? There's the waveguide. So is there any way you can modify the waveguide?
That's a good question. So a lot of people, not everyone does high harmonics in waveguides. And so you can look at the different geometry that you use, and then you're going to end up with a different set of terms down here. But the conclusion is going to be more or less the same. It's always somewhere, for 800 nanometers, it's always somewhere around 150 eV. It's going to be the best you can do. Okay, so we're going to take a different approach. Rather than increasing the laser intensity, we're going to keep that fixed and increase the laser wavelength because in the cutoff rule you can see that the scale is like lambda squared. If you think about the three-step picture, again, if your electron spends more time oscillating in the laser field, it's going to gain more energy once it's returned, and so you're going to get to a higher cutoff photon energy. So instead of starting at 800 and generating harmonics to 100 eV, we're going to take it the other direction. We're going to start at 800 and actually go to much longer wavelengths first, which is going to let us get to much shorter wavelengths eventually. And so, this simple cutoff rule was proposed a while ago, and it's been pretty well understood. It's probably like the easiest equation you've ever seen. So why didn't people realize that they could do this before? And so if you come and look at, and again, there's been experimental results. This group, roughly 10 years ago, compared the harmonic spectrum at 800 nanometers with the harmonic spectrum at 1.5 microns, and showed the cutoff extended from somewhere around 60 EV out to somewhere around 150 EV. And again, this paper is 10 years old, so people have understood this for quite a while. The problem is this cutoff doesn't tell us, this scaling rule tells us the cutoff. It doesn't tell us how bright it's going to be. And so to understand that, so actually kind of the simple picture to think about this is really your electron is a quantum mechanical object. So as you go to a longer laser wavelength, it spends more time accelerating in the laser field before returning to the atom. So it gets more energy. But because it's a quantum mechanical object, it starts inside inside this atom, and it's fairly well confined. And then as soon as you remove it from the atom, it's going to start to spread. The wave function is going to start to spread. And so the more time it spends away from the parent ion before returning, the more it's going to spread. And then you're going to have the overlap between the electron wave function and the atom when it returns is going to go down very quickly. And so these are 2D quantum mechanical simulations kind of simulating this process. It's supposed to be an electron wave function. It is an electron wave function as it goes through this ionization and high harmonic process. And so you don't have to understand all of it. But the important point is that 0.8 microns, you get these nice strong fringes. Whereas when you scale up to 1.3 microns, they're very smoothed out because the wave function of the electron is spread quite significantly. And so the single atom yield from quantum mechanical simulations scales at something like lambda to the minus 5.5. But what we're going to argue is that while the single atom scaling doesn't look very promising, actually if you consider the full phase matching picture, you can still come out ahead. And so here's just some calculations. Again, This is based on this is just based on that delta K equation that I showed earlier. You can calculate for the three main gases we use, helium, neon, and argon, what the phase matching photon energy is going to be as a function of driving laser wavelength. And so the key here is that you get to much higher photon energies for the same laser intensity. So you reduce the ionization and you can still phase match. And you can, for 2 microns, you're already up to about 500 EV, well, through the water window, and 3 to 4 microns, you're phase matching at around a keV. And here's the simple picture for the argument for why the macroscopic picture can still be favorable. So in high harmonic generation, you're kind of in this different regime where your harmonic generation medium is actually strongly absorbing the harmonics you generate. And so this always kind of puts a clamp on the absolute efficiency of the process, because the length of your medium is limited then not by the phase matching, but by where you start to reabsorb the harmonics more quickly than you're generating them. And so for argon and neon, as we go to the higher photon energies to phase match the higher photon energies, it has these inner shell absorption edges that drop that transparency quite a bit. We think will ultimately limit how far we can go with them. But with helium, as you move away from the extreme ultraviolet and into the soft X-ray, it becomes much, much more transparent, which would make it possible to do a longer harmonic generation medium. And so then you get more atoms adding up coherently, which makes up for the fact that you have each atom is emitting less. So here's a simple picture of our experimental setup. We take just a standard Ti-Sapphire chirp pulse amplifier. It's got about 20 millijoules at 800 nanometers and 25 femtoseconds. Again, this is a 10 hertz source, so keep that in mind later. And we pump a 3-stage optical parametric amplifier. And at the output, we have a signal beam centered at 1.3 microns with about 5 millijoules at about 30 to 40 femtoseconds, and an idler beam at about 2 microns with about 2.5 millijoules at like 35 femtoseconds. Then we take the output of the OPA, focus it into our hollow core waveguide. And here we've got a picture of one of our current setups. Right here, these two places are the inputs for the gas. And then our waveguide is this bright little thing in the middle here. It's got the laser going through and it's generating the plasma, so you see the plasma emission. And then at the output of the waveguide, we're going to have our soft X-ray beam that will either send through a spectrometer or shine on our sample. So this is that plot, again, that I showed a couple minutes ago. We're plotting the photon, the highest photon energy we can phase match as a function of driving laser wavelength. And over here, I marked, I know everybody's used to thinking about fractions of a keV, the different wavelengths that corresponds to. And so for each of these three main gases, helium, neon, and argon, we've got a curve for the predicted phase matching cutoff. The solid one corresponds to using a 3-cycle laser pulse, and the dashed one to using an 8-cycle laser pulse, since that changes it slightly. And then at the bottom, we're going to plot our results for the different driving laser wavelengths. And so this is a typical result for argon. And so what we're plotting here is each of these lineouts is going to be a plot of our high harmonic spectrum. And then we're going to take our high harmonic spectrum as a function of pressure. Because as I mentioned, the way we understand how this phase matching works is through the pressure dependence. And so we get a lot of information out of it by plotting it in this way. And then in each spectrum, you're going to see there's going to be kind of 2 regions. There's going to be one side that's you can see the harmonics brightly, and they're going to increase as we increase the pressure, peak, and then fall back off. On the other side, you can't. I don't know if you might be able to see one harmonic here. If we plotted this on a log plot, you'd see there are still harmonics on this side. It always kind of looks like a barrier. There's always one side where we see harmonics that are bright, another side where they're there, but they're not very bright. And so we're going to draw a line at this barrier, and we're going to call that the phase matching cutoff. And then we're going to plot that data point on this curve. And so that's how we're going to fill in our experimental data points along this curve. And so for argon, with 800 nanometers, the phase matching cutoff is at about 50 eV, and the phase matching pressure is at about 30 torr. Then when we increase to 1.3 microns for argon, the phase matching cutoff jumps up to about 100 eV, which fits well with what we predict. And also notice that the phase matching pressure has gone up from 30 torr now to about 150 torr roughly. So the reason for that is as we go to these longer wavelengths, the index of refraction of the gas for the longer wavelengths is lower. So you have to increase the pressure more to balance the contribution of the gas with the phase velocity in the waveguide. And so for helium already at 1.3, our spectrum is extending into the water window above about 100 eV. There's always this little dip in our spectrum here. Shows that we're above the carbon edge. That's just always there because there's some carbon contamination in our spectrometer. And so then we use our Euler beam at 2 microns and can repeat the same experiments. And for helium, now it's already spanning the full water window up to about 520 eV. And neon's already well into the water window as well, up to about 400 eV. And notice the values here, up to 9,000 torr, which is it's about 12 atmospheres. So you can see some of the technological challenges in making this work. And so here's a line out of the peak for both helium and neon here. And we estimate the flux is about 10 to the 5 photons per shot in a 1% bandwidth for helium. And if you're not used to thinking about this number, that's about 3 orders of magnitude brighter than the next highest cited number for high harmonics in this energy range. But yeah, again, so we've got the carbon edge always shows up in there. It's kind of nice because it shows that you're in the water window, but you also always lose part of your spectrum. And these are pretty brand new results. Tenio and Ming Chang just went to Vienna where they did a collaboration with a group that built a 4-micron laser. And they brought our spectrometer and the high harmonic setup out there and did phase matching with that. In helium, it extends up to about a keV. And in neon, up to about 900 eV. And these are both pretty interesting for doing work near the magnetic edges of some of the ferromagnets like nickel and cobalt. But I want to come back to the water window stuff where we did that 2 micron. And so we wanted to use the water window harmonics we were generating to do some first kind of demonstrations that now they're becoming bright enough to be useful. So we did kind of one of the simplest experiments you can do, which is repeat this 200-year-old Young's double slit experiment. And of course, you put in, just put in a double slit and you measure the interference. It's relatively simple, but it's certainly not easy. And so remember, like I said, this is a 10 hertz laser source. Most of the work we do in the group for the applications experiments are done on a kilohertz, where you've got 100 times improvement in flux just due to the rep rate. We're using central wavelength around 4 nanometers. So you need very small features in your sample to get enough diffraction to actually get into the far field where you see interference, some reasonable distance away from your sample. So we set up. The setup we did was we just focused our laser into our waveguide, and at the output of the waveguide we put in 2 metal filters, and then we have our sample drawn out here, and then just measure, which we shine the full spectrum after those metal filters onto the sample, and then measure the diffraction pattern. So here's our results. And so here is the diffraction pattern we measured, and then we did a simulation of the diffraction pattern, again assuming some bandwidth to our spectrum, and then also the right distances to the CCD. And so, by eye they look pretty similar. We see that we're missing these orders here, which is just due to the fact that you're overlapping the single slit diffraction pattern on top of the double slit interference pattern. So this is the first zero of the single slit diffraction pattern. And so what's pretty, we do see full fringe visibility, which tells us that the spatial coherence is good. But what's kind of more important in my mind is that I worked on a project in a similar energy range when I first started, where we were taking the other approach, the high laser intensity, to hit it as hard as you can and get some harmonics out of these high energies. And the problem is, whenever you try to do something like this, and we did try to do similar experiments, you always have the harmonics are so much brighter at the relatively long wavelengths, that it's really, really difficult to isolate the short wavelength harmonics. And so in this case, just by using 2 thin metal filters, we're able to get rid of all of the low order harmonics and the fundamental light, and just actually see a diffraction pattern that's due to the short wavelengths, which is going to be really important for being able to actually use these for imaging applications, and anything where you aren't going to spectrally resolve the harmonics immediately after. And so the reason we're able to do this is there's kind of 2 main reasons. One is we're actually phase matching at these wavelengths now, so that keeps them relatively bright. And the second comes back to this issue of the transmission. And so if you look at helium and neon, they become much, much more transparent as you move to the higher photon energies. And at the same time, we're going to very high pressures, so it becomes even more dramatic. So our harmonic generation medium itself is acting like a filter to get rid of all of the low energy harmonics, which makes it relatively easy to filter out whatever's left after that. This was featured PRL recently. So we did this the same thing with our helium spectrum, just sent it straight in. You notice it's pushed more towards the shorter wavelengths, so you would expect the fringe spacing to be reduced, which is what we see in this line out. And you're already starting to see some issues in the visibility, which are just due to the fact that we don't have enough pixels to fully resolve the fringe. So we'd actually have to go another half a meter to a meter away. We're already near the end of our optical table. Okay, so now we've demonstrated that we have this spatially coherent, ultra-fast beam and we've shown this in a few regions now, at 30 nanometers, 13 nanometers. Now we've extended it down to 3 to 4 nanometers. Again, it's reasonably it's bright and it's useful for a variety of applications. And I'm not going to talk about most of these. This is the COSI seminar, so we're going to come back and look at imaging again. So Matt gave a talk about this just 2 weeks ago, so I'm not going to go into too much detail. Feel free to ask questions about it later if you're interested. But basically the issue with, one of the challenges with doing soft X-ray imaging is always the optics. And this is, if you work with even visible light microscopy, you'll probably be familiar with this. In principle, you're limited by the wavelength of the light that you illuminate your sample with. But of course, in practice, you need to have good lenses, good objectives. I mean, people spend a lot of money on really nice objectives with many optical elements that correct for all the aberrations and form a nice image of your sample. And so you can imagine as you go to the soft X-ray region of the spectrum, it gets harder and harder to make optics with that low of level of aberrations. So you're generally limited by the optics and not by the wavelength that you're using. And so we use these. An alternative to that is to just measure the diffraction pattern. You get rid of all the optics after the sample. Then you use these iterative methods to retrieve an image of the object based on the diffraction pattern. So there's a lot of convenient features of these. Again, limited, in principle, it's just diffraction limited. And it's insensitive to vibration too. So here's a picture of the simple setup that they use over in that lab. It's our femtosecond laser, focus it into a gas, and then send it into the chamber where it's focused on the sample and measured on a CCD. So the nice things are it's a very convenient, simple setup, and it's also very small. This all fits on one optical table. So Matt showed these results a couple weeks ago, and so they're able to get near wavelength limited resolution with this technique. And so what we're excited about is taking that and combining it with these shorter wavelength sources that we've been developing, and being able to push the resolution towards 10 nanometers by using these 3 nanometer sources. So a good question is how does this coherent diffractive microscopy compare with using an objective lens and an incoherent source, especially in the water window where you're looking at biological samples. So there's some convenient aspects of working with the more traditional optics. You can use incoherent illumination, which is generally easier. And you can also don't have to deal with retrieving this iterative phase retrieval problem to reconstruct the image. You can just directly measure the image of the sample. But one of the major issues is, so this group wrote a paper recently where they did a signal to noise comparison between the two techniques. And what they found was that due primarily to the fact that these objective lenses are always really inefficient, you actually need much fewer photons incident on the sample in the case of the coherent X-ray imaging in comparison to the more traditional incoherent bright field imaging. And so if you remember that we're using ionizing radiation at this point. So if you can reduce the dose of X-rays on your sample while you're trying to image it, obviously that kind of helps out a little bit. So the other thing that we pulled out of this paper was they do an estimate of the resolution, the number of photons you need incident on your sample for a given resolution in your image. And so we went through and did kind of a feasibility estimate. And actually, with our sources upgraded to a kilohertz, we'll be able to do cellular images in something like a few minutes. So here's another example application where we're going to take advantage of these elemental absorption edges. So this group took this sample. It's a silicon crystal with some bismuth buried inside, some structure to that. And so if you stick your spectrum either right above or below the bismuth edge, and you can take an image in either case, you end up with these images that are, again, mostly the silicon structure, but the difference between the two of them is going to be whatever's any of the bismuth buried inside. So by looking at the difference between these two images, you can actually image the structure of this element inside of this bigger picture, and using soft X-rays is kind of a unique way to get that information that otherwise would be lost. So one more on the application side. In the process of developing these, I mentioned a few times, we really need to get to a kilohertz to start pushing the applications further. And so we've been developing this laser system that'll have enough pulse energy for us to pump the OPA and also run at kilohertz repetition rates. And so once we have that in place, we can take it kind of a different way. And so there's other groups who've taken these similar high pulse energy lasers, typically at lower rep rates. And when you start with so much energy in your driving laser, you can keep the conversion efficiency roughly constant and get out very bright harmonics in a single shot. And they're able to demonstrate single shot imaging again with something like 100 nanometer resolution. And so once we've got this system that has both the high pulse energy and the high repetition rate, it'll be possible to use this kind of thing for dynamics, where we can take single shot images, pump a sample, and either watch heat flow, watch magnetic domain switch, or plasmas. And here's the setup of the system we're planning to build. It'll be a long focus so that you get very bright harmonics out. So in conclusion, we've shown that by going to this infrared phase matching, we can extend the phase matching cutoffs and harmonics into the soft X-ray, and demonstrated that we can actually use this for experiments. So in the future, we'll be able to combine this with the current imaging setups that are being developed in the group to have unprecedented spatial and temporal resolution, which is going to open up applications in single-shot imaging, dynamic magnetic switching, nanosystems, bioimaging, heat flow, a variety of things. Thank you.
We have time for questions.
Question about the imaging.
Yeah.
Typically, the resolution that you report is something like a factor of 2 times lambda, and that sort of seems to be a general rule that I see from some of the results. In optical microscopy, we're used to seeing lambda by 2, and divided by 2 as the resolution criteria. Is this purely a result of having a restriction on the numerical aperture, the effective numerical aperture that you had, since now you're doing the diffraction pattern, you're presumably in the far field, you have to be a given distance away from the object? Is that too much of a...
Sorry.
What is the limiting factor that's making it 2 times length?
Okay. Yeah, thanks. So the question is, why are we stuck at around twice the wavelength? So it's always a question of numerical aperture. And so in this sort of scheme, the numerical aperture is going to be defined, it's either how close you can physically get your camera to the sample, and also how you need a lot of flux to scatter. Right, the numerical aperture is going to be, how high can you measure signal above the noise, at what angle, and so that falls off. The signal out there falls off pretty quickly. Actually, these guys could tell you more about it, I think. Part of what they're running into now is that the approximations we make, that this is just, if you have the right phases, it's just a Fourier transform. As you start to go to higher and higher numerical apertures, it's really a 3-dimensional Fourier transform and not a 2-dimensional Fourier transform. And so it becomes a more complicated reconstruction. And so that's what they're finding. I mean, they've got data that goes beyond this. I don't know how much I should say. I don't want to get in trouble.
More complicated, but definitely doable, right? Well determined, with the transform.
You end up with fringes due to stuff happening in the depth as well. So it's not, you can't just do a simple 2D reconstruction of the what you end up with is like, look off extra basically, wherever the sample stops, and then you go to really tiny microaperture, that's focus is really small. So then you surface layer and you see diffraction effects, and so
Is that?
Sure. So is the functioning rule then sort of like a rule of thumb like 2 lambda for X-ray constantly?
Well, so the main thing, one of the main things is you need to fulfill the solar sampling requirements. You have to have dense enough pixels to be able to see the diffraction pattern. And so it sort of depends on the size of the sample.
What kind of beam quality do you have?
At the 3 nanometer wavelength, or
Yeah, sure.
we haven't been able to measure it quite as well.
Do you
It
have a
looks.
qualitative feeling for it? Good enough for everything you tried to do?
I mean, so we know that when we do, when you have it phase matched for an extended distance at these longer wavelengths, it's quite nice. We've sort of seen it through when we were doing the spatial coherence measurement, but it was also got a little bit clipped on the way, so it wasn't.
I can't remember your optical setup. Do you have like collimating optics after it comes out of the tube?
No. So we did at one point. I didn't show that result. We did at one point. I mean, refocusing and collimating are difficult at these. We were able to. We have a multi-layer mirror that was made at Berkeley. And we were able to refocus the short wavelength light. And by then it's kind of astigmatic, just the geometry we had at the time.
Pretty hard to get materials at that wavelength.
Yeah. So the index of refraction is going to be basically 1. The absorption is always high. So you either have to do it with diffractive optics, where you block things out with the, or you have to do reflective optics.
Right.
And they can make pretty good multi-layer mirrors to
How
about.
much reflectivity can you get with your
So these ones that if you want to do near normal, at 3 nanometers, we have pretty nice, like kind of cutting edge ones that are about 20% reflective.
Okay.
So everything's pretty not. You lose a lot of light of anything you put in. At 13 nanometers, you can do really well, and that's why the semiconductor industry is pushing hard there.
Okay.
You can get up to like 70%.